Hello, everyone. Today we will be talking about one of our last two statistical analyses for the semester. We are getting very, very close to ending the semester as we're approaching the conclusion of this term. And as you've noticed, as we've continued on down the line of introducing new statistical analyses, we've been getting a little bit more complex in terms of the way that we've been introducing them. There's a lot of material that we end up needing to cover, and there's good solutions that we have to look at in terms of what the purposes of these statistical analyses are really used for. Because remember, the purpose of statistical analyses are ultimately to test predictions and to answer research questions that we have associated with the specific topic. So in our particular case, in our previous week, we were discussing the issue of independent and related samples t-test in the case where we were comparing two groups. So for instance, you were comparing men and women, you were comparing pre-test, post-test scores on a specific dependent variable. But what happens in the case where you may encounter a situation where your independent variable of interest has many levels or many groups? So in the case where you just don't have two groups, like in the case of a t-test where we had a dichotomous variable, what happens in the case where you have multiple groups? And that's really where analysis of variance really comes into play. So for this lecture, I'll be introducing analysis of variance and what analysis of variance is used for and how it's actually calculated theoretically. We're not going to be going through an actual calculation of a hand calculation of this formula because it is way too complex and it would take so much time. It would take over 30 minutes for you to do one question. And that, unfortunately for me, I just feel that that is just too much time to be spending on one question for a homework assignment or for an exam. With t-test, it's a little bit more manageable, but even for ANOVA, it just becomes very, very unmanageable. And again, to be honest and to reiterate kind of what it is that I've been talking about all semester long, the majority of the time you're going to be using statistical package software such as SPSS or other SAS, for instance, or even Excel that are going to calculate these types of statistical analyses for you and are going to be helpful for you to answer your research hypothesis and to answer your research question that you have. So ultimately here, what I want to do is I really want to just make sure that we understand what the purpose of analysis of variance is, what the underlying concept of the formula is. So we're going to look at the theoretical components associated with it. I'm going to present a situation or an example of a case where we would want to use analysis of variance, provide you with the statistical information already for a completed analysis of variance technique. So we're not going to run through again the equation, but I'm just going to give you the answer at the end. And then we're going to interpret that information and discuss how it is that we found that information and came to specific conclusions. So again, the application portion also of using the statistical formula. Now, the second part of our lecture is going to be in regards to what we're going to call factorial ANOVA, and we're going to be discussing the purposes of using more than one independent variable. All right, so let's set up a quick example here for ourselves. So if we were going to think to ourselves, all right, what would be a case in where we would have an independent variable, again, a predictor, an influencer, that may potentially have more than two groups or more than two conditions or levels? And here we may have a situation like the following, that we may have a question such as, what are the effects of anxiety on exam performance? Or on a memory test or whatever the case may be. So let's say, for instance, that we have three levels of anxiety. We have high anxiety, we have moderate anxiety, and we have low anxiety. So participants come into our research situation and we give them a questionnaire that's evaluating their anxiety levels. And we either classify them as high anxiety, moderate anxiety, or low anxiety. And here in our particular case, I'm going to say that I have 10 individuals per group. Okay, so I have 10 individuals in my high group, 10 individuals in my moderate group, and 10 individuals in my low group. So now here, ultimately, what we're doing is we're saying we are now having three levels of that independent variable. So now I'm going to be introducing this term levels in terms of statistical analyses and how it relates to the idea of the independent variable. And all that the term levels refers to is the number of categories with the independent variable that we're dealing with. So if we think back to our independent samples t-test from last week, we talked about two levels or two groups. So we talked about the male and the female group. We talked about the high stress, the low stress group. We talked about pre-test, pre-test, post-test groups. All of those would also be considered levels. So the pre-level, post-level, male level, female level, high level, low level. So all of that essentially just means the same term. So we use that term synonymously. So using level, group, or condition, they all really mean the same thing. So in our particular case, we have three categories or three levels of anxiety: high, moderate, and low. So in our particular case, we may ask ourselves the question, okay, well, we learned about t-test in the previous weeks. Why can't we not just use a t-test then? So why can't you just compare high group to moderate group, high to low, and moderate to low? And that's actually a very good question, right? So why is it that I just can't do three separate t-tests comparing first high to moderate and only high to moderate on exam performance or on memory scores, moderate to low, and then high to low? Why can't I just do that? And the reason and the answer to that question is the following: that if we end up using too many statistical analyses to answer one specific research question, such as the one that we have right here, we may potentially inflate the probability of committing a type 1 error. Because remember, in our previous discussions associated with type 1 error, the issue of alpha level, we talked about alpha level always being set at the maximum, right? Or we would ideally want to set it at the maximum, which would be 0.05. So if you now have a t-test, such as in the case that we did in our previous weeks, we set in our t-test an alpha level associated with it. And we would normally say that the alpha level associated for that one single t-test would be set at 0.05. So in other words, when you were comparing males and females on anxiety levels or on aggression or whatever it is that we were comparing them on last time, here in that particular case, that specific test for comparing men and women would have an alpha level set at the maximum, right? Because you want to maximize the probability of finding a true effect. So in other words, maximizing power. So in our particular case here, if we were to do one t-test comparing high to low, that's an alpha level that we would set at the maximum of 0.05. If we now did moderate to low, that's another alpha level at 0.05. And then if we did high to low, which would be our last comparison, we would again set another alpha level at 0.05 because you're doing three separate t-tests, right? Because you're comparing now only two groups in those specific cases. If that were the case, that you would end up doing three separate t-tests to compare all of these individuals, that becomes problematic to us. And the reason it becomes problematic is that when I add up all my alpha levels, I now add up across all the different statistical analyses that I've done. So in my particular case, I now have an alpha level set at 1.5. So 15% or 0.15. So here that exceeds the limit of 0.05 that we've been allowed to have in the behavioral sciences, and this is too much of a probability of committing a type 1 error. So too great of a probability of incorrectly rejecting the null hypothesis. So using multiple t-tests to answer this specific question would not be appropriate. And it wouldn't be appropriate because, again, it's going to reflect the issue of increasing my alpha level, because in each one of my comparisons, again, high to moderate, high to low, and moderate to low, each one of them I would want to maximize power, setting my alpha level at 0.05 in each case, thus increasing my alpha level too high. So now you may be asking yourself, all right, well then why don't you just set your alpha level lower in each one of these comparisons so that way you never exceed the 0.05 level? And you're absolutely right. That is exactly what it is that we want to do. And how is it that we're going to do it? We're going to do it using our analysis of variance technique, because its purpose is ultimately to control that inflated alpha level that we may potentially have by using multiple t-tests. So now what it's going to do is it's going to adjust the alpha level to do one test that's going to compare high to moderate to low. So essentially here, what our analysis of variance technique is going to do is it's going to compare all three groups to each other while making sure that my alpha level is never exceeded. And I'm going to talk about how it actually does that in just a couple of minutes here. So when we think about this decision tree that I've presented to you in previous weeks, where is it that we're at now in terms of our statistical analysis? Well, again, remember, we're wanting to compare groups, right? So we're wanting to see if there are significant differences between our groups. In our previous weeks, we were over here with our two groups because we were comparing males and females, pre and post, high and low. But now we have multiple groups. So now I have the case where I am talking about using high, moderate, and low. So I have three groups now. So in this particular case, since I have multiple groups, I now have to come down here and find what it is that I'm talking about. So again, just as we did with our independent samples t-test, we now have ANOVA techniques that are either independent samples or related samples. With independent samples, just as we talked about with the t-test, we have groups that are mutually exclusive. Okay? In the case where you have groups that are mutually exclusive and you have one independent variable, you're going to use a one-way ANOVA. So in our particular case here, we were talking about having the effect of anxiety on exam scores. So in our particular case, we have one independent variable and we have one dependent variable. My independent variable in this particular case is my anxiety, because again, those are my categories of high, moderate, or low, and my exam scores are what I'm measuring my participants on. So in our particular case, I have mutually exclusive groups, so people who are going to be in the high group, people who are going to be in the moderate group, and people who are going to be in the low group. Different individuals. Since they are different individuals and I only have one independent variable, such as I have here, I want to come down here and use a one-way ANOVA. In the case where I would have multiple independent variables, like we will talk about a little bit later on in our lecture, we are now going to be using a different type of ANOVA technique, and we're going to talk about that in just a little while. But for our purposes here, right now we want to concentrate on this issue of using a one-way ANOVA. So now, if you wonder to yourself, why do you call it a one-way ANOVA? I mean, what's that? The reason it's called a one-way ANOVA is because of the term that we use that's called wayness. Wayness for us in statistical language means the number of independent variables. So that's what wayness refers to, the number of IVs, okay? The number of independent variables that you're working with. So in our particular case here, that we are working with one independent variable, we call it a one-way ANOVA because it's one independent variable ANOVA that we're going to be using. That's why we call it a one-way ANOVA. So the term way, whenever it is that you see it, and I'm going to be using it a little bit later on in our lecture, that I'm going to say things like a two-way or a three-way or a four-way. What do those refer to? Those refer to the number of independent variables. So here when I use the term one-way ANOVA, that just means one independent variable. So just keep that in mind, all right? Okay, so here are our scores for our particular example, right? So we were talking about the effects of anxiety on exam performance or on memory score, whatever the case may be, and here are our scores. So group 1, which is going to be my high stress group, has a scores of 2, 3, 2, 3, 2, and an average of 2.4 for them. Moderate has an average of 4.6, and low has an average of 6.6. So here what I want to do is I want to know, do my groups significantly differ from each other? So just as I asked with an independent samples t-test or with a related samples t-test, are there significant differences between my groups? Because that's the question that I'm asking. Here, that's the exact question that I'm asking. I'm just dealing with more groups. So here I'm asking the question, are there significant differences between my three groups? Now here, I talk about three groups, but three groups are the minimum to use an ANOVA technique. If we have three groups or more, you always want to use an ANOVA technique. Always. If you have three or more groups. If you have two groups, you're always going to use a t-test. Always. You will never use an ANOVA technique with only two groups. Okay? You're never going to do that because the ANOVA technique has different assumptions than the t-test technique. Okay? You would never really want to use a different statistical analysis to answer a different question. So in our particular case, if we have three or more groups, so for instance, if we would have had high, moderate, low, and very low, you still would have used an ANOVA technique because you have three or more groups in that particular case. So the question that I'm asking here is there a significant difference? So is there a significant difference between the groups? Between my three groups in this particular case. Okay? So here, that's the question I want to answer. So how am I going to do that? Again, my t-test wouldn't work because my t-test would ultimately inflate my alpha level, because in each one of those particular cases, I would end up using 0.05 as my maximum alpha level. So thus, I'm going to end up with 0.15 alpha level for my entire comparison of high versus low, moderate versus low. But rather here, what I'm going to do is I'm going to try to modify and use a different statistical analysis that's going to control for that alpha level. Okay, that's ultimately what ANOVA is really going to be used for. It's going to be a method for us to control the alpha level so it doesn't exceed the maximum that we're allowed to set it at and still compare all my groups. That's ultimately what we're doing here. So what I want to do, I want to compare my scores of 2.4, 4.6, and 6.6. That's ultimately what I want to do in this particular question, because I want to test my specific hypothesis, for instance, and whatever my hypothesis may be. So for instance, we may predict that people in the high stress group are going to perform worse on the exam than people in the low stress group. Well, what about the people in the moderate stress group? Are they going to perform better or worse in the high stress group? Are they going to perform better or worse in the low stress group? So here I'm trying to make as many comparisons as I possibly can in my situation. So what is the F-test going to tell us? And when I use the term F-test, I'm talking about ANOVA here. So just because I use the term F-test, don't think I'm talking about something else. I just talk about the F-test because the statistic that's given to us by ANOVA is my F-stat. Okay, that's the statistic that's going to be given to us by our ANOVA. So that's why we call it sometimes our F-test. So what is the F-test going to be telling us, and what's it going to be predicting? So ultimately, an F-test is essentially asking the following question. Is there a significant difference between any of the groups that I'm comparing? And again, minimum of 3 groups. I can have more than 3 groups, but a minimum of 3 groups. So here in our particular case, it's asking the question, is there a significant difference between high, low, or moderate anxiety groups on exam performance or on memory score or whatever your dependent variable is going to be? So here in our particular case, that's the question it's asking. Is there any difference between those 3 groups? Now you'll notice here we have some old friends of ours, our null hypothesis and our alternative hypothesis. The null hypothesis predicts the following. The null hypothesis predicts that group 1 is going to be equal to group 2, which is going to be equal to group 3. So in other words, all groups are going to be equal to each other, and the difference between the 3 groups is going to be equal to 0. So just as it was predicting in our t-test and in our z-test, the null always predicts 0. So in other words, here the null is predicting no difference. That's what the null hypothesis is predicting, no difference. No difference between who? Between group 1, group 2, and group 3. Now here you'll notice that I'm not using the average for the sample. So I'm not using capital M or X bar, but rather I'm using mu. Why am I using mu? Because remember, the null and the alternative always refer to the population because they refer to the effects that exist out there in the real world. Who is the real world? The population is the real world. So here, another way to write the null hypothesis would be mu1 minus mu2 minus mu3 would be equal to 0. So just the way that we've written the null hypothesis before, here again we're writing it the same way, but now you'll notice that we're adding in another group. Now another way that you'll normally see the null hypothesis written, as the following. Mu1 is equal to mu2, which is equal, there we go, to mu3, and then it'll say dot, 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 equal to 0, and the reason it has the dot 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 is because, again, remember that ANOVA assumes that you have 3 or more groups, minimum of 3, but you may potentially have more groups. So in the case where you were to have more groups, let's say 4 groups, 5 groups, 6 groups, here you would continue to say mu1 is equal to mu2, which is equal to mu3, which is equal to mu4, which is equal to mu5, etc., etc., etc. All right. Now, if you're asking yourself, well, what's a situation where you would have more than 3 groups? I mean, that seems very unlikely. Well, think of things like education level. You're a junior, senior, you're a freshman, sophomore, junior, senior, or other. So you may have 5 categories. You could have different ethnicities. So you're Hispanic, you're African American, you're Caucasian, etc., etc., etc. You have multiple ethnicity, so you're going to have multiple groups in that particular instance, different personality types, et cetera, et cetera, et cetera. So you're going to have these situations where you're going to have an independent variable in some cases where you have more than 3 groups. So in those particular cases, you would still want to use an ANOVA. That's why we leave it open with dot, dot, dot. Now, the alternative hypothesis, the exact same thing in terms of mu1 minus mu2 minus mu3 is going to be equal or not equal to 0. So in other words, the difference between the 3 groups are not going to be equal to each other. Thus, the difference between them is not going to be equal to 0. Now, since I told you that ANOVA provides us with the F-stat, the F-statistic for the null hypothesis is going to predict that the F-stat is equal to 0. For ANOVA, for the alternative for ANOVA, the F-stat is predicted to not be equal to 0. So always remember that. The null always predicts 0, no matter what and no matter what your statistic is. The alternative predicts that ANOVA would not be equal to 0 or your F-stat would not be equal to 0. Okay, that's the main question here that's being asked. But now, if you notice here, in terms of the question that's being asked by ANOVA and by the null and the alternative hypothesis, it's comparing the 3 groups. But here you'll notice that it's not specifically telling you, well, how do I know that group 1 isn't equal to group 2, but that it is equal to group 3. So maybe group 1 and group 3 are equal to each other. There's no difference there. But maybe group 1 and group 2 differ, and maybe group 2 and group 3 differ. What happens about that? I didn't see that written here. In the case where you would assume that group 2 would be different from group 1 and group 3, it would assume the alternative hypothesis, because the alternative hypothesis is just assuming the groups are not equal to each other. Which groups? Any of the groups or some of the groups. That's essentially what it's saying. So the alternative hypothesis is kind of tricky here, that it's saying none of the groups are equal to each other, or in some cases, some of the groups are not going to be equal to each other. The null always predicts that all the groups are equal to each other. So in this particular case, and this is a new term that I'm going to introduce, do not freak out on me, but this is a new term. The term that we use here is that the ANOVA test, the overall ANOVA test, provides what's called an omnibus test. Omnibus test. What is the term omnibus referring to? The term omnibus test refers to, are there differences between any of the groups? That's what the question is going to ask. Are there differences between any of the groups? So going back to that question right there. So the omnibus test asks the question, are there differences between any of the groups? The question here, you'll notice here, I have not asked the question, is there a difference between group 1 and group 2? I haven't asked that. But here I'm just saying that, is there a difference between group 1, group 2, and group 3? So are there differences between any of the groups? That's what the term omnibus means. It means an overall test for significance. So what ANOVA is going to do, ANOVA is going to tell you, do the groups equal to each other or do they not equal to each other? But it's not going to tell you specifically who is not equal to each other and who is equal to each other. So again, very, very important, and listen very closely to what I'm saying. The ANOVA test is not going to tell you which groups specifically differ, if they differ at all. All that the ANOVA test is going to tell you is there a difference between the groups or is there no difference between the groups? Which groups? I don't know. But here I'm telling you there is a difference between the groups or no difference between the groups. That's all that it's going to tell you. So here the overarching question, well then how do I know which groups specifically differed, if they did differ at all? Well then we have to do an additional statistical analysis that we are going to talk about that we call post hoc analyses, so analyses done after the fact, for us to confirm which groups specifically differed or which groups did not specifically differ. Okay? That's what we're going to do here. Which groups specifically differed or which groups did not specifically differ. So again, key here, ANOVA, the overall test for ANOVA, is ultimately telling you, do the groups differ or do they not differ? It's not discriminating which groups specifically differ from each other or which groups don't differ from each other. All it's doing is it's just saying, yes, the groups differ, or no, the groups don't differ. So many times people make the mistake of saying, well, my ANOVA test was significant. I rejected the null hypothesis. My statistic landed in the region of rejection. So the groups differed. Well, then we asked the question, well, which groups specifically differed? Oh, well, I don't know. Well, yeah, of course you don't know at this point because you don't know that information because ANOVA doesn't tell you which groups differed. So there is a possibility that group 1 and group 2 may be equal to each other, but group 1 and group 3 may differ. That is a possibility. So if any of the groups, any of the comparison of the averages differ from each other, ANOVA will automatically become significant. Okay, that's the key. If any of the averages differ from each other significantly, so again, if group 1 and group 2 don't differ, but group 1 and group 3 do differ, ANOVA will automatically say the groups differ. But then it's not specifically telling you, but it really only differs between group 1 and group 3. So here it's a little bit tricky, so you got to be careful with the way that we actually interpret the ANOVA statistic here, and we're going to again work through that. Okay, so the formula for the F-test, what does it look like? I'm not going to show you all the ins and outs of the formula because again, we're not going to calculate it because we're not going to spend time. It's just too convoluted to do it. If you want to take an intermediate statistics course, or an advanced statistics course that we offer here at our institution, we'll be more than happy to work through the formula itself. Or if you take a graduate level statistics course later on, you will definitely do it by hand. But for our purposes here, I just want you to understand the conceptual issues associated with ANOVA. So in our particular case, what is the ANOVA statistic? The ANOVA statistic is classified as a ratio of the variability between the groups versus the variability within the groups. So if you're asking here, okay, great, I have no idea what you're talking about. Ultimately, this is the way your textbook discusses the ANOVA statistic, which is the correct way of discussing it. So ANOVA statistic is essentially the variances between the groups in my numerator divided by the variances within the treatments or within the groups. So here, another way of saying it is the following. The differences, including any treatment effects, divided by the differences between no treatment effects. If you want to think about it in another fashion, the way that you can think about it is the way that we've talked about it many times. Effect variance divided by error variance. So what I've done here for you is I've decided to interpret this formula and this ratio a little bit more specifically so that way it's more understandable. So this is the way that we actually describe the F statistic, so the way that we actually calculate it. It is the MS between groups divided by the MS within groups. What is the MS between groups? The mean squared between groups divided by the mean squared within groups. What does this mean again? Because you're probably like, I'm completely lost. This is the way that we understand what ANOVA does. So this is the logic behind ANOVA. ANOVA tests the following. Is there less variability within the groups, but more variability between the groups? So in other words, what ANOVA is doing is it's saying the following. If we have less differences within the groups, so in other words, scores are more similar to each other within the groups, but there are more differences between the groups, then we would expect the groups to differ because of my manipulation or my control. All right? Now you're probably thinking to yourself, I have no idea what you're talking about. So let's go back here to our data. So essentially what ANOVA is going to do, ANOVA is going to say, all right, within the groups, is there a lot of spread within the scores? Okay? It's going to ask that question. So within the groups, within all three groups, is there a lot of spread within the scores? If the answer is yes, there's a lot of variability, a lot of spread, a lot of differences within the group. So within the high stress group, is there a lot of differences within the values? Within the moderate group, is there a lot of dispersion? Within the low group, is there a lot of dispersion? If the answer is yes, then the denominator of my formula is going to be high. All right? Because remember, what we're dealing here is we're dealing with the between groups differences, there we go, divide that by the within groups differences. So in other words, we're saying if there's a lot of variability within these numbers, and within these numbers, If there's a lot of variability within each one of the groups, this number will be high. If there is not a lot of variability within these groups, so in other words, what's another term for variability? Variance and standard deviation. If the variance and standard deviation within the groups is low, we would expect then that my statistic would be higher, because my statistic, my F value, is made up of the between groups differences divided by the within groups differences. What are the between groups differences? They are my averages. So in other words, what ANOVA is really trying to do, ANOVA is trying to say, look, is there a difference between my averages? Okay? If there is a lot of difference between my averages, that number will be high. If there is a lot of difference within my numbers, within my groups, so if there's a lot of spread within each one of these groups, this number then will also be high. If that number is high and that number is high, my F value is probably going to be low. Okay? Because again, my denominator is high. But if the difference between the groups is high and the difference within the groups is low, then I'm going to expect my statistic to be high, to be large, is essentially what we're saying. So again, it goes back to that idea that we talked about with power, effect variance divided by error variance. So in other words, what we're saying here is that the numerator of the F statistic is effect variance, the denominator is error variance. Just as we did with our T statistic, that we talked about effect variance divided by error variance. In Z, we talked about effect variance divided by error variance. The same thing here. What is effect variance? I'm assuming here it's the differences between my groups, because that's the only thing that I'm in control of. That's the only thing that I can assume would have changed these scores. The error is essentially going to be those individual differences, or that there's a lot of spread within the scores. So in our particular case, that's the logic of ANOVA. What we're saying here is, if there is less variability or less differences within the groups, so the more similar that scores are to each other within the groups, but more variability between the groups in terms of the group averages, not between the group scores, between the groups averages, then the groups would differ due to my manipulation or control. So again, in other words, if this number is low, so if the within value is low and the between number is high, I'm going to expect my F value to be high as well. That's the logic behind ANOVA. So again, we're not going to calculate it by hand, because again, it's going to take quite a lot of time to do it by hand, but rather I'd rather have you understand the conceptual idea behind what ANOVA does. If you want some additional information associated with what the F ratio really means, read your textbooks. The textbook does a very good job of discussing what your F ratio really means. So now, what are the assumptions associated with our ANOVA? So just as we had with our t-test, that we had specific assumptions associated with our statistical test, what are the assumptions associated with ANOVA? The assumptions associated with ANOVA are the following. Number one, we have scores that are quantitative in nature. So in other words, again, we have to have numbers as my dependent variables. So in other words, I have to have interval or ratio scale data that I'm going to test my individuals on. So I need to collect numbers. I can't have narrative responses. I cannot have qualitative data. My dependent variable scores per group need to be normally distributed. So in other words, the scores for my high stress group need to be normally distributed. The scores for my low stress group need to be normally distributed. The scores for my moderate group need to be normally distributed. We also have equal variances across the groups. So in other words, we have homogeneity of variance assumption again, right? Or what we also call heterogeneity of variance assumption in some instances. And what that means is that we have variances that are equal across the group. So in other words, the standard deviation or the variance score for group 1 is equal to the variance score of group 2, which is equal to the variance score of group 3, or there should be no significant differences between them. And last, our observations should be independent of each other, both within and between. So in other words, between my groups should not be mixed together. So I shouldn't have high, low, and moderate. I should really keep them separate from each other. And within my high group, I should not have them copying from each other. Within my moderate group, they should not be working with each other. And within my low group, they should not be working with each other. So again, if you notice here, these assumptions are the exact same assumptions as we had for our t-test. The only difference between T and ANOVA, T was using 2 groups, ANOVA is using 3 or more groups. All right, so how do we know if we have differences between our groups? Now, if we want to really answer this question, we really have to do what are called post hoc analyses, or what we also call pairwise comparisons. Now, in the case where you were following along with your textbook, you'll notice that in the discussion of the pairwise comparison section or the post hoc analysis section, the author of your textbook makes note that there are many different types of post hoc analyses that are able to be used, or pairwise comparisons that are being able to be used, such as Tukey's analysis, LSD's analysis, and other types of analyses. So here, since the author already discusses those different types of analyses, I want to introduce one that he really doesn't use, but that's one that's a very typical post hoc analysis or a pairwise analysis that's used in different psychology disciplines as well. And this is actually what we call our Bonferroni correction. Now, our Bonferroni correction works just like any other pairwise comparison test. Now, remember, the idea here that we have is the following. We've done our overall analysis of variance test, right? So we go back to this idea of, okay, I did my overall ANOVA test. So I compared to see if there were any differences between any of the groups. But now I need to know what groups specifically differ. So in this particular case here, what we want to do now is we want to go through and we actually want to compare moderate to high, we want to compare moderate to low, and we want to compare high to low. So in other words, our original ANOVA test only compared high to moderate to low. So across the board, across the 3 groups, are there any differences between the 3? So when I look at the 3 averages, I would have expected that the 3 averages would have been equal to each other, thus the difference between the 3 averages would have been equal to 0. But here now I'm assuming that there was a discrepancy. So now the difference between the 3 values was not equal to 0. So now I need to identify who specifically is creating the difference. So is the difference existing between the high score and the moderate score? Is the difference between the moderate and the low score? Is the difference between the high and the low score? So who really differs? That's the idea of a pairwise comparison. Now, for our purposes here that I want to discuss, I want to introduce this what we call a Bonferroni correction. Now, why is it that we actually have a correction? The issue that we have here is the issue of committing a type 1 error. So again, going back to our discussion that we had at the beginning of the lecture, that, well, why don't you just do 3 separate t-tests to look at the difference between high and moderate, moderate and low, and high and low? Because remember, in each one of those instances, we would assume then that we would set an alpha level for the t-test at 0.05. So we would set it at the maximum to try to ensure that we would have power set at the max for each one of those particular statistical comparisons. So in our particular case here, I now want to go through and I want to compare to see if there is a specific difference between high and moderate, high and low, and moderate and low. But to do this, I now need to correct for that issue of potentially increasing the probability of committing a type 1 error. So in other words, I need to adjust my alpha level to really make sure that I don't exceed the 0.05 maximum that I have available for me in terms of my overall statistical test. So in our particular case, what we need to do is we need to make an adjustment to our alpha level per comparison. So in other words, rather than us saying for high and moderate comparison, I'm going to have an alpha level of 5%, and then I'm going to have an alpha level at 5% for moderate and low, and an alpha level for high and low of 5%. Rather, I need to create an adjustment to this alpha level value so that that way, when I add up all 3 alpha levels across all my comparisons, I don't exceed the 0.05 maximum. So here, I have to think about this in the back of my mind that this is the max that I can have it at. So if I'm going to have these 3 separate tests that all come about from using my comparisons, I cannot exceed 0.05 when I add all three of them up. That's why I need to make this adjustment to the alpha level. So the way that we're going to have our new alpha level being created for us is that we're going to take our maximum alpha level that we want to set. In our particular cases, I want it to be a 0.05. That's the maximum I'm allowing it for all three of them together. Okay, so again, all three of them together have to add up to 0.05. So what I'm going to do is I'm going to take my alpha level of 0.05 and I'm going to divide it by the total number of possible comparisons that I'm going to be making. So in my particular case, I had an independent variable that has three groups. So I had the high, the moderate, and the low. So when we look at all possible number of combinations or comparisons, we have high versus moderate, high versus low, and moderate versus low. Those are all my possible combinations that I have. So I have three possible combinations. So in this particular case, what I want to do is I want to look at the number of groups that I have. So in our particular case, I have what we're going to now classify as letter K. K refers to us in ANOVA to the number of groups. So I have the number of groups, in this particular case 3, high, moderate, and low, and I'm going to take my alpha level and divide it by the number of comparisons. So I need to know the number of groups to know the number of comparisons that I'm going to make. So in other words, if there are more than 3 groups, let's say for instance we had a very low group down here, now the number of comparisons changes because I have high to moderate, high to low, high to very low, moderate to low, moderate to very low, and low to very low. So now I have 6 comparisons, 1, 2, 3, 4, 5, and 6. So here, knowing my number of groups is going to be very important. But now you'll notice here that we are not dividing alpha level by K. We're dividing my alpha level by the number of comparisons. That's the very important issue here that we need to address. So if we had 4 groups, like in the case that I've presented to you here, we wouldn't divide my alpha level by 3 because now the number of comparisons is increased, it's actually doubled to 6. So in our particular case here, what we need to do is we need to create a new alpha level that's going to be 0.05, because again, remember, that's the maximum that I've set it at, and we're going to divide by 3 because that's the number of comparisons that I had when I had 3 groups. I have 3 comparisons. So again, high to moderate, high to low, and low to high in that particular case. If I had 4 groups and I had 6 comparisons, 0.05 divided by 6, now all of a sudden we have a difference in terms of my alpha level. So if my alpha level here is now going to be split by 3 comparisons, we're going to do 0.05 divided by 3 comparisons. Now each comparison gets, rather than 0.05 alpha level, they get 0.016 alpha level. So the comparison of high to moderate, there we go, gets an alpha level equal to 0.016 or 0.017, whatever it is that you want if you want to round off. Moderate to low gets 0.016 as well. And then last, high versus low also receives 0.016. So when we add up 0.016 plus 0.016 plus 0.016, we are going to receive our alpha level total equal to 0.05. So in our particular case here, we want to make sure that we adjust our alpha level in our pairwise comparison portion to make sure that we are going to be able to add up to an alpha level of 0.05. So thus, I have to divide my alpha level by the number of comparisons that I'm going to make. So thus, if I were to then look on my critical value sheet, I wouldn't look under the critical value for an alpha level of 0.05. I would have to look for an alpha level of 0.016 because that's the alpha level for that specific comparison. Okay, and that's a very, very important issue here that we needed to talk about. So again, your textbook talks about other types of tests, Tukey's test, LSD tests that are available for you. All of them have pros and cons. The one I like to use is I like to use the Bonferroni test. On the exam, if I were to give you a question about pairwise comparisons it would more than likely come from the Bonferroni correction, because that's the one that I like to personally use in terms of my statistical analysis. That's the one that I got trained on for many, many years. So again, now looking at our scores, remember my omnibus test was essentially going to compare my three averages. Because remember, that's what my overall ANOVA test was going to do. It was going to compare my three averages. So it was ultimately going to identify, is there a significant difference between the groups? If yes, great. If no, great. If the null is true, then I have to just stop there. If the null is true, where the groups don't differ, there's no point for me to go through and do a post hoc analysis. So I'll say that again. If the null is true, so if the null is true, there is no point to doing this, okay? We would not do that. And the reason is the following. If my analysis of variance technique, my overall analysis of variance technique, the one that compared group 1 to group 2 to group 3, if at that point my statistical analysis says no differences between the groups, why do I have to go in there and confirm that no differences existed? Because that's what the pairwise comparison is going to do. So my analysis of variance technique, my overall analysis of variance technique is telling me, hey, there's no difference between high, moderate, and low. The pairwise comparisons would only confirm that, because it would compare high to moderate, which it would tell me no difference, high to low, no difference, and moderate to low, no difference, thus confirming the null. Because here, the null hypothesis had already told me that no groups would differ, the post hoc test would tell me no different. Now, if the alternative is true, okay, so if the alternative is true, in this particular case, I do want to do the post hoc analyses. So in other words, if the null is true, where the analysis of variance technique is telling me the groups differ, but again here, I don't know which groups differ. That's what this is telling me. It's telling me which groups specifically differ from each other. So in other words, potentially group 1 and group 2 may differ, but group 2 and group 3 may not differ. So again, if we look here at our data, we may find that we may say, oh wow, so if I compare group 1 to group 2, they may differ. Group 1 to group 3, they seem to differ. But what about group 2 to group 3? Well, they may not differ. Perfect. In that particular case, the ANOVA test would have told you that the alternative was true. The ANOVA test would have told you then that the alternative was true, that the groups do differ. But again, which groups specifically differ, I don't know that. So here, using my post hoc analysis is going to help me identify which groups specifically differ from each other. And that's the goal that we're trying to get at here. So if the ANOVA test is telling you the groups don't differ, the null is true, there's no reason to do a post hoc test. But if the ANOVA test is telling you the groups do differ, then I have to do my post hoc test to identify specifically which groups differ from each other, because not all the groups may differ. I don't know that from my overall test of significance. So again, looking at our results, and here, these are the actual results that we would get from our data. So here, I've already gone ahead and calculated the ANOVA test for you. And again, I actually didn't even do this by hand. I wanted to make sure that I was able to do this for you just the way that we would really do this in statistical testing, is that I use my computer software program to look at the data and compare my results. So whenever it is that I did my statistical software analysis, this is the result that I get, okay? So this is the output that I receive in my statistical test. So even if I were to do this by hand, this is what I would end up with in terms of my statistical analysis. So just like with our t-test, that we put it into the format of the statistical test, here I'm doing the same, but now what I want to do is I need to know what this means for me. So in other words, in comparison of all three groups, so when I compare group 1, group 2, and group 3 to each other, not individually to each other, but across the board, so looking at the three groups across the board, my overall ANOVA test indicated that there was a significant difference. How do I know that? I know that by looking at this here. I look at this format. Now you're probably thinking to yourself, okay, what does this format mean? This format is essentially indicating to the reader the groups differed. Which groups differed? I don't know. Okay? That's what I have at this point. So in other words, how do I know if my overall ANOVA test is significant? How do I know if the groups do truly differ? I look at this right here. What do I look at specifically? I look at the p-value. Remember that p-value that we've talked about so much? There's the p-value again. In this particular case, p is less than 0.05. What do we conclude about the null when our p-value is less than 0.05? Well, we conclude that the null is false. So in other words, the groups do differ from each other. That's what we found statistically speaking. Which groups? I don't know. But here at least I know that the groups specifically differed. So here what I'm going to do is I'm going to show you how it is that I ended up with this information here and how I format all this information into this specific format that we have here. Are we going to go into depth to talk about the pairwise comparisons and to show you how each one of those differs and how they're calculated? And to be honest, I'm not going to do that at this point because that's going to be for other courses that you may take in the future. But for our purposes, I do want to show you at least how we do this specific identification that ANOVA indicated that the groups do differ. Which groups differ? I don't know. Again, I don't know that information yet, but all I do know is that the groups do differ at this point. So what we need to do is if we were to get only this information, okay? So if we were only to receive my statistic of 13.51, so if we did the formula that's in your textbook, or if we actually went through and did this all by hand, my F value would be equal to 13.51, okay? That's what my F value would be equal to. So I need to now look to see if my statistic lands in the region of rejection or not. So I need to find my region of rejection for my distribution where the ANOVA is true for the null hypothesis. Okay, how am I going to do that? I need, again, my critical value. For my critical value, I need my alpha level. I need my sample size or my degrees of freedom. And I need to do a one-tailed test. Now here you'll notice that I've been talking about so much one-tail versus two-tail test, one-tail versus two-tail test. The ANOVA or the F distribution, okay, so where the statistic of F comes from, so the F distribution is positively skewed. So our distribution looks like the following. The lowest value that you can have in that distribution is equal to a 0, and then you only have positive values. So you actually have a positively skewed distribution. So here, there is no negative tail that you can look at. There's only a positive tail that you can look at. So thus, with ANOVA, you never have to deal with a one versus a two-tail test. You always deal with a one-tail test because there's only one tail for you to look at. This is the only time that we do this, and it's for our F distribution. For T, we had two or one-tail test. For Z, we had a two or a one-tail test. And for our next statistic that we're going to talk about later on at the end of the semester, our correlation coefficient, that one also uses a two or a one-tail test. F distribution, our F statistic, only uses a one-tail test. Now, again, to find my critical value, alpha level, sample size, and the number of tails. Now here, there is one other piece of information that I need to find my critical value that's different from what we've ever been talking about. For the F distribution, aside from knowing my sample size, I also need to know what K is equal to. So remember when I talked about K about one or two slides back, that I talked about K equaling the number of groups? I now need to know what K was equal to in this particular case. So I need alpha level, sample size, K, and this one-tailed distinction here that I'm going to make. All right, so I need to find my critical value. So we need to perform null hypothesis significance testing. And I know you guys are like, oh, no, I thought we were done. Like I told you all, we're not going to be done with null hypothesis significance testing until we're done with the course. We're going to continue to bring this up over and over and over again. All right, so now let's actually perform null hypothesis significance testing. But before we do that, let's talk about what all these numbers mean, because we need to figure out this information, specifically sample size and this idea of K. We need to figure it out, and this information is actually given to us right here in parentheses, and I'm going to talk about how we actually get that information. Okay, so when we look at the F statistical information, the way it's formatted for us, this is the way that it was formatted for you in the previous slide. So this is the actual results from our data of high, moderate, and low anxiety individuals on exam performance. So in our particular case, what does this information mean for us, right? Because we're going to be reading research articles one day, and we're going to look at this information and we're going to say, I have no idea what any of this means. How do I interpret this information? So just as we did with our t-statistic that I showed you, this is the way that we interpret this information. Here I'm going to do the same. So the first thing here that we have to look at is we have to look at what this letter represents, our F. Our F value is the statistic or the ratio that we got by comparing the between groups effect divided by the within groups effect. So what I talked about in the previous slides about the MS between divided by the MS within, that's the exact same thing that I'm talking about here. So that's what it refers to. This F is the F statistic, my F value or my F ratio. Next, we have what's in parentheses. We have now the value of a 2. The first value here that we have in parentheses is what we call degrees of freedom denominator, or also degrees of freedom between groups. How do we calculate degrees of freedom numerator or degrees of freedom between groups? This is equal to k minus 1. So remember that we've talked about degrees of freedom many times before, and we continue to talk about n minus 1 because of standard deviation, that was the denominator in standard deviation. And then in t-test, we took n total minus 2. Here, we're doing the same thing, but since we're dealing with more than 2 groups, part of the ANOVA statistic wants to know how many groups were you actually dealing with, and how many degrees of freedom between the groups do you have. And the way that we identify that is by having k, which is equal to the number of groups that I have. In my particular case, it was 3 groups, high, moderate, and low, minus 1. In this particular case, giving me a value equal to a 2. That's why I write this value of a 2 here. So if I were to ever ask you, how many groups did we have in our study, and all you received with this information, all that you would have to do is take this value and add 1. Because remember, to receive this value here, to get this value here, you need to have the number of groups minus 1. So now add 1 to this number here, and that will give you the number of groups. That would equal k, the number of groups that we would have in our study. The next number that we have here is our degrees of freedom within groups. Our degrees of freedom within groups are essentially my total sample size, so n total minus k. Now here you're asking yourself, okay, well wait. We've always been so accustomed to doing n total minus 1 or n total minus 2, depending on the statistic that we were working with, right? In standard deviation, we took n for the group minus 1. In t-test, we took n total minus 2. We took 1 from group 1 and 1 from group 2. So why are you now not taking n total minus 3? And technically, you are. And the reason for that is because k refers to the number of groups. So in other words, we took n minus 1 for group 1, n minus 1 for group 2, and n minus 1 for group 3, because we had 3 groups in our particular case. So here, in reality, we are taking n minus 3 because we had 3 groups. But here, rather than saying n minus 3, we say n minus k because k changes depending on the study that you're doing. So in our particular case, k refers to 3 because I have 3 groups that I was comparing. But what happens in the case where I had high, moderate, low, and very low? That's n minus 1 for group 1, n minus 1 for group 2, n minus 1 for group 3, n minus 1 for group 4. So that would be n minus 4. So n total minus 4. So in our particular case, we had a total of 15 individuals, 5 for group 1, 5 for group 2, and 5 for group 3, minus k. So total sample size of 15 minus 3, giving us a value equal to 12. We also call this second degrees of freedom here degrees of freedom within groups, or degrees of freedom denominator. Degrees of freedom within groups or degrees of freedom denominator. So you'll notice now that the term degrees or between groups and within groups, remember that with our F ratio, the between groups, the MS between groups was in the numerator. That's why we call them degrees of freedom for the numerator. And in the denominator of the F ratio, we had MS within groups, and we called them degrees of freedom denominator because they're the ones that refer to the denominator of our equation. The next thing here that we have is my statistic, my actual value, which is 13.51. So this is the value that I obtained from doing my omnibus statistical test. So in other words, this is my overall statistical test that compared the three groups. I'm not comparing group 1 and group 2, group 1 and group 3, group 2 and group 3. I'm comparing group 1, 2, and 3 to each other. So across the board, I'm comparing them. That's the statistical value that I received for this specific test. So in our particular case, F values can only be positive because remember, my distribution is positively skewed. So in other words, the lowest value that I can have in my distribution is 0, but I can have positive values. I cannot have negative values for an F ratio. So here I have to have 0 or greater in my particular case, but now if we were to find no differences between any of the averages, so in other words, comparing group 1's average to group 2's average to comparing group 3's average, in that particular case, if there was no difference between those values, I would have expected my F value to be 0, because if all the averages are equal to each other, the numerator of my formula would be equal to 0, divided by anything would be equal to 0. So 0 divided by anything is 0. So if that were the case, where there would be no significant differences between any of the averages, then I would have expected F to be equal to 0. Now the last thing here is my p-stat. My p-statistic, remember, this is the probability that my statistic of 13.51 in this particular case occurred solely due to chance. So here we're saying that the probability that 13.51 occurred due to chance was less than 0.05. Now again, remember, here whenever it is that we do our statistical testing and we come up with this format, we're expecting here that if p is less than 0.05, that means that my statistic of 13.51 should have landed in my region of rejection. So when I found my critical value and I began my region of rejection, I'm assuming now that my statistic of 13.51 landed in the region of rejection. So thus confirming that I rejected the null hypothesis. So whenever you read this format here, as we did with our independent and related samples t-test, if p is less than 0.05, we're assuming here that your statistic landed in the region of rejection, so thus there are differences between the groups. All right, so how do we go about finding my critical value? So here what I've done for you, I've essentially provided for you a critical value sheet associated with ANOVA. You can find this in the back of your textbook. The one here that I provided for you, I like this one a little bit more because it really gives you information as to how to actually use the table, and then gives you also an example of, okay, well, let's say for instance, you were going to have this specific value or you were going to have that specific value. The only thing I don't like about this specific table here, or this handout that I've given you, is that it uses incorrectly this term right here. So it says P is equal to 0.05 level of significance. I've told you many times that P is not equal to alpha level. And in reality here, what they mean is they mean alpha level. So here, always make sure just to think that this actually is in reference to alpha level rather than p-value. So never think about it as actually being your p-value. It's the actual alpha level that we're actually talking about here. So this level of significance refers to alpha level, and this refers to alpha level as well. Here what we want to look at is we want to look at some of the following information. So the way that this table is formatted for you is it gives you two separate tables. The first table is actually given to you with alpha level set at 0.05. And then at lower ones, we have alpha, this is our critical value table for an alpha level set at 0.01. Because remember, you're in control of alpha level for the omnibus test. So here, we are not talking about having done the Bonferroni correction. We have not made any adjustment to our alpha level. So don't think that that's what we're doing here. We are still in the process of doing our ANOVA test, our overall ANOVA test. So the overall one. We're not doing the Bonferroni correction. We're not doing Tukey's test or LSD or anything here at this point. We're doing our overall analysis of variance technique test. So in this particular case, we would assume that we're doing the very first hypothesis test. So since we're doing an overall test of significance, comparing my three averages, again, I need to know my alpha level. I need to know my sample size. So I need to know my degrees of freedom and my degrees of freedom within groups, which is really what I'm looking for. I also need to know my degrees of freedom between groups. And I also am going to look at this one tail issue. Now here, the good thing about this table is that since we know that the distribution is going to be positively skewed and the lowest value that we can have is a 0 and there's only one tail that we can look at, we never have to worry about this issue of, well, I'm saying it's a one-tailed test versus a two-tailed test. It automatically assumes that it's a one-tailed test. So it's assumed here that we have a one-tailed test. Okay, we always assume that. We don't have to worry about this two-tail issue here in this particular case. So here, going back to our example from our high, moderate, and low anxiety levels on exam performance, my degrees of freedom between groups were a value of a 2, and my degrees of freedom within groups were a value of a 12. Okay, so I'm just going to keep those in mind. So a value of a 12 and a value of a 1. A value of a 2, sorry. So a value of a 2 was my between groups value, my degrees of freedom between groups. My within groups was a value of a 12. Okay, so in our particular case here, now our table actually goes on to explain exactly how we're going to use these two degrees of freedom, because you'll notice now that we have values that go across that are in yellow and also go down, up and down, also in yellow. So we need to know what they refer to. Now, what we're referring to here is the ones that are in yellow going across. So going across first, this is what we're going to have our degrees of freedom between groups. Okay, so these are degrees of freedom numerator in our particular case. Going vertically here, we have our degrees of freedom denominator, or our degrees of freedom within groups. Okay, so again, going vertically, so going up and down, we have our degrees of freedom within groups. So in other words, we have n minus k to identify our degrees of freedom within groups. And going across in yellow, we have our degrees of freedom between groups, which are going to be k, the number of groups, minus 1. So in our particular case, we know that the degrees of freedom between groups is equal to a value of a 2. So we're going to go to our value of a 2, because remember, this is our degrees of freedom between groups. And we now need to go and find degrees of freedom within groups. So we go to our column for a 2, degrees of freedom between groups, and we're going to go all the way down until we find degrees of freedom within groups. So there is my critical value. My critical value for our specific test is 3.89. Okay? Now, why is it 3.89? Because remember, I want to maximize my alpha level. I'm a conservative researcher. I want to try to maximize the probability of me finding an effect if an effect does truly exist out there in the real world. So how do I go about doing that? I go about that setting my alpha level at 0.05. If you want to set it lower at 0.01, you would just go down to this table down here where we have our alpha level set at 0.01. Again, you go to the 2 column for between groups, you go to the 12 column for within groups, and now you'll notice that your critical value jumps from a 3 point some odd, 3.98 I believe, to a 6.93. So it jumps up quite a bit. And why does it jump up? Because remember, it's making your region of rejection smaller, because it's pushing your critical value further away from 0. So in our particular case, I want to try to maximize power. So I'm going to leave alpha level at 0.05. So again, my between groups degrees of freedom was equal to a 2. Within groups degrees of freedom equal to a 12, giving me a critical value of 3.89. All right, so now what's the next thing I want to do? The next thing I want to do is I want to do null hypothesis significance testing. I know you hate it, but we're going to do it again. So here, we're going to have our distribution. Remember that this distribution for the F distribution, what is it going to look like? It's not going to look normal. It's going to look positively skewed in our particular case. So it's going to look like that. And down here, we're going to have a 0 value set for my critical value, or sorry, set for my minimum value for my distribution. So ultimately, the F distribution where the null hypothesis is true assumes that the difference between the 3 groups, in this particular case, high, moderate, and low, the difference between the 3 groups would be equal to 0. And why would that difference be equal to 0? Because it assumes that there's no difference between them. That's the idea of the null hypothesis. So again, since the null hypothesis predicts no difference, and it assumes then that the numerator is looking at the difference between the 3 groups in terms of their averages, we're now going to assume that if that difference is equal to 0, 0 divided by anything is going to be equal to 0. So we found that my critical value for an alpha level set at 0.05, degrees of freedom between groups was equal to 2, degrees of freedom within groups was equal to 12. We found my critical value equal to 3.89 3.89, we're going to go and find 3.89. So here I'm just going to label it here. So I'm going to say this is my critical value of 3.89. So my statistic was not 3.89. My stat that I calculated in my study was 13.51, if I'm not mistaken. Let me just confirm here very quick. 13.51, perfect. So 13.51. So here, where does 13.51 land? So if this is my critical value, and this is the beginning of the region of rejection, I find that 13.51 lands somewhere way over here, right? Really far into the region of rejection. So here, what would I expect my p-value to be? Well, p, since it lands in the region of rejection, would be less than 0.05. Now here, it's probably even less than 0.01 because it falls very, very deep within the region of rejection. But at least here to play it safe, since we are not looking at the unit normal table, we're just going to say that p is less than 0.05. Because remember, whenever it is that we say is p less than 0.05, we always say reject the null. So in our particular case, we're rejecting the null hypothesis because my statistic landed in the region of rejection. P less than 0.05 confirms that. So when I did my statistical test using my statistical software, it essentially did this for me. Now, on the exam, for instance, if I were to give you an example of this, what would I do? I would give you something like this, that I would give you the format for the statistic, ask you to find the critical value, and identify if the statistic lands in the region of rejection or not. So do we reject or do we retain the null hypothesis? So in our particular case, we've rejected the null hypothesis. So in other words, groups differ. That's what we're going to conclude. The groups differ. Which group specifically? I don't know. So which specific group? So is there a difference between high and low? Maybe. Is there a difference between moderate and low? Maybe. Is there a difference between moderate and high? Maybe. I don't know. All I know is that the groups differ, but I don't specifically know which groups differ. So if we wanted to do our post hoc analyses, our pairwise comparisons using our Bonferroni correction, that's when we would really want to use our statistical analysis software packages. That's why I'm not going to show it here, because that's above the scope of this particular course. When you guys begin to take research methods, intermediate statistics, and advanced statistics, you'll begin to use it at that point there. All right, so the next issue here that we have is the following. What happens in the case where we have multiple sessions for participants? Or can we have a situation where we have a participant being in the high, being in the moderate, and being in the low? So in other words, rather than us saying, is there a way for us to only keep individuals in separate groups, can we now have individuals be in all the groups? And the answer is definitely yes. So just as we did with our repeated measures t-test, we also have what's called a repeated measures ANOVA. So just as I demonstrated to you on the decision-making tree, and here I'll go very quickly here to the decision-making tree back for us, if I can get there. There we go. Rather than us saying, are the groups independent from each other, we're now saying, are the groups related to each other? And in our case, yes, the groups are definitely related to each other. So thus, we're going to do a repeated measures ANOVA. The independent samples one-way ANOVA for one independent variable assumed that our groups were mutually exclusive from each other. So in other words, people in the high, people in the moderate, and people in the low were different from each other. They're different people. Now we're saying, can we have the same people in all the groups? Or can we have pre-test, post-test, and then post-post-test? And the answer is yes. We can definitely do that with the repeated measures ANOVA. The only requirement, again, is that we have multiple testing conditions. So in other words, you have to have them in the high, have them in the moderate, and have them in the low. Or you give them pre, you give them post, and then you give them a post-post test. So you have to have at least 3 measurement times. That's what we want. So when we use a repeated measures ANOVA, what does this mean? Ultimately, what a repeated measures ANOVA is going to do for you is it's going to compare your averages across the same individuals. So in other words, it's going to assume that the same people are in all 3 groups. So let's say, for instance, Brittany. Brittany is going to be in the high group, in the moderate group, and in the low group. She's got to be in all 3. If she's not in all 3, I can't use Brittany. She's got to be in all 3 groups. Or she's got to be in the pre, in the post-test and in the post-test. So she's got to be in all the conditions. Or, for example, think of the following situation. Think about, for instance, for me, that I would say, oh, well, I want to see how different formats or styles of learning in the classroom may potentially affect exam performance. So I'm going to use different styles of performance or different styles of presentation. So what I'm going to do is at the beginning of the semester, I'm going to use only PowerPoint. So all you guys do is you come into the room and I turn on the PowerPoint and I have you read what's on the PowerPoint. I don't talk at all, which would be very, very boring, right? Next, so I give you an exam. So after we only do that, I give you a test. I bring you back, and now all I do is just talk, no PowerPoints, no visual presentations, nothing. Then I give you an exam. Then I bring you back again for a third trial or a third group, and now you're in the online course where we only do online course information, and I give you an exam. So now I'm going to compare your scores across PowerPoint only, verbal only, and online only. So I'm going to compare you across all three to identify if group differences exist. Now, another big question that we come across is we come across this issue. Can we have a situation where we have more than one independent variable in our experiment? And the answer is yes.